Jealous of Mr. Rita, Mr. Smith decides to get into his car and go on vacation as well. A cylinder in the piston of his car contains gas at a temperature of 30 degrees Celsius with a volume of 1.45 cubic centimeters and a pressure of 110,000 pascals. What will the final temperature of the gas be if it is compressed to 15 hundredths of a centimeter cubed and its pressure increases to 1.75 times 10 to the 6 pascals? Okay, so the first step is to write down our givens. So we know that the pressure is starting out at 110,000 pascals. We also know that the temperature is starting at 30 degrees Celsius. Now we have to be careful. We need temperature in Kelvin, so we have to add 273 to this. So 30 plus 273 is 303 Kelvin. The volume is 1.45 cubic centimeters. It does not matter what units the pressure and the volume are in as long as they're consistent, but temperature must be in Kelvin, so that's why we had to convert this, okay? And Kelvin is equal to Celsius plus 273. What will the final temperature of the gas be? So the final temperature, that's what we're trying to find. If it is compressed to 15 hundredths of a centimeter cubed, and its pressure increases to 1.75 times 10 to the 6. So here you have to remember some scientific notation. We need to move the decimal point 6 spots to the right. So I'm going to move it 2 spots to get it to the other side of the 5, and then 4 more, so I need 4 zeros. So 1, 2, 3, 4 zeros. So we have 1,750,000 pascals. And our equation is pressure 1 times volume 1 over the number of molecules 1 times temperature 1 equals pressure 2, volume 2, number of molecules 2, temperature 2. Now, we got this by solving for Boltzmann's constant, and then in all of our problems, the number of molecules always stays the same, so we never use that, okay? But it is there in case you would encounter a problem at some other point that does have it change. All right, so now we just need to substitute in. So our pressure is 110,000 times the volume, 1.45, divided by the temperature in Kelvin, so 303, equals the pressure, 1,750,000 pascals, times 15 hundredths of a centimeter cubed, divided by temperature, which we don't know. So how we solve this is we simply cross multiply. So I'm going to take all of these things and multiply all three of them together. So I'm going to take 110,000 times 1.45 times temperature 2. I'm going to take all three of those things and multiply them together. So 303 times 1,750,000 times 0.15. And again, multiplication is commutative. So if you put the 303 at the other side of this, it doesn't matter, okay? 110,000 times 1.45 is 159,500 times temperature 2. And then if I multiply 303 times 1,750,000 times 0.15, I get 79,537,500. Divide both sides by 159,500. And we get temperature 2 is equal to 498.67 Kelvin, which I'm just going to round that to the nearest Kelvin, which is 499 Kelvin. Before beginning a long trip on a hot day, Mr. Smith inflates his automobile tire to a pressure of 1.8 atmospheres. So pressure starting at 1.8 atmospheres. At 293 Kelvin, so look at that. We're already in Kelvin, we're not going to have to convert. At the end of the trip, the tire pressure has increased to 2.1 atmospheres. assuming that the volume of the air inside has remained constant. So we don't know what this volume is, but we know it's the same for both. So you can let it be equal to a variable like V, or you can make it 1 or 2 or whatever number you want. As long as you make them the same, your equation will work out. What is the temperature? Okay, so we're going to use our equation. P1 V1 over N1 T1 equals P2 V2 over N2 T2. Again, number of molecules stays the same, so we can cancel those out. This time volume is staying the same too, so we can just cancel those out to begin with. So we've got P1 over N1, T1 equals P2 over T2. And again, a pressure can be in whatever units as long as it's the same for both. Temperature didn't have to be in Kelvin, but it was already in Kelvin, so we don't have any conversions to do. So we have 1.8 over 293 equals 2.1 over temperature 2. Again, we're going to cross multiply, so we have 1.8 times temperature 2 equals, that's a 2.1, so 293 times 2.1, 2. So 1.8 times temperature 2 equals 615.3. Divide both sides by 1.8. Temperature 2 is equal to 341.83 Kelvin, or to the nearest Kelvin, 342 Kelvin. Okay, our last problem. Mr. Freed, the Earth and Space Science teacher at CCHS, asked Mr. Smith to check the weather conditions for him while on vacation. Therefore, Mr. Smith set up a weather balloon designed to expand upon ascension. The initial volume of the balloon upon liftoff is 3.2 meters cubed. When it is filled at a pressure of 1 atmosphere and a temperature of 300 Kelvin. All right, temperature's in Kelvin, we don't have to worry about it. What is the volume of the balloon when the pressure drops to 0.05 atmospheres and the surrounding temperature is 190 Kelvin? So we're good, we don't need to do any conversions. These match, those are in Kelvin, good to go. So pressure 1, volume 1 over number of molecules 1 times temperature 1 equals pressure 2 times volume 2 over number of molecules 2 times temperature 2. So we have 1 atmosphere times 3.2 meters cubed. Again, number of molecules stays the same. So we have temperature 1, 300. Other side, we've got the pressure is 0.05 times volume is what we're trying to find over 190. So we cross multiply. So I've got 1 times 3.2 times 190 equals 300 times 0.05 times volume 2. 1 times 3.2 times 190 is 608. 300 times 0.05 is 15 times volume 2 divided by 15. Volume 2 is 40.53 meters cubed, and online I just rounded it to 1 decimal point, so it says 40.5 meters cubed. There you go.